Hey everybody, this is Mr. Ainsworth. We're going to get into Lesson 8 here and talk about what's called the Trapezoidal Rule for approximating the area under a curve. Okay, and so what we want to do is switch from rectangles to trapezoids. In previous lesson we did it with rectangles, and we used the left endpoint approximation method, we used the right side, and we used the midpoint. We discovered 3 different ways to do that. But what's better than all 3 of those is using trapezoids. So let's start off with a general function, and let's call this function f of x right here, and let's find the area underneath the curve from x equals a, call this point A here, to b, let's call this point B here. These are going to be the upper and lower limits of our integral pretty soon. But let's suppose that we're trying to find the area underneath the f of x here and above the x-axis from A to B using trapezoids, not rectangles. Okay, so what we first want to do is divide it up into equal parts, or n equal parts, or intervals. To do that, well, let's write that down first. We want to divide the interval from A to B. So divide the closed interval from A to B into n equal parts, okay, or intervals, so that we can use some trapezoids to approximate the area underneath the curve. Okay, so let me just draw some intervals in here. Let's draw n intervals. So let's divide them up like so. They have to be equal width too. So I'm trying to draw them in such ways so that they have equal width. There we go. And instead of topping off each one from the left using rectangles, or from the right using rectangles, or even from the midpoint using rectangles, what I'm going to do is wherever they meet the function, let me switch to red here, like right here and here, wherever they meet the function, I'm going to connect them. And it's obviously going to be at an angle there because we have a slope curve, and I'm going to top them off in trapezoids. Okay, so I divided up into parts here with equal width, and I need to determine the width of these intervals, which is going to become the height of the trapezoid. We know that for trapezoids, let me talk about trapezoids for a second. You're familiar with them. They have 4 sides, but 2 sides are parallel, like this right here. And or if it's rotated and the parallel sides may be vertical, it may look like this right here, where these 2 sides are parallel. So the bases B1 and B2 are parallel, and the other 2 sides are non-parallel. So we actually have the second case here that's highlighted. We have trapezoids that are orientated vertically where the bases are parallel vertically. Okay, and we have to remember that for trapezoids, that the area is the height divided by 2 times the sum of the bases B1 plus B2. That's for any trapezoid, where again the bases are parallel, so B1 is parallel to B2. Okay? So for us, since these vertical lines are all parallel, these vertical dotted lines right here are the bases. Okay, and the other 2 are not. So these trapezoids are orientated vertically. The distance between the dotted lines, these vertical lines, is the height of the trapezoid, or the width of the interval. Okay, and we have to, let's write that down. Okay, so this is h here, the height of the trapezoid. So h is equal to height trapezoid, and we have to come up with a way to find that height. Now we want to divide the distance from A to B into n equal parts. Because of that, the height is the distance from A to B, which is found by taking right endpoint minus left, so B minus A. And if you divide it into n equal parts, that distance h has to be B minus A divided by n. So the height is B minus A divided by n, and that's the height of the trapezoid, or the width of the interval. Okay. Okay. Now let's talk about these heights. starting from the left endpoint here at A, that height I'm going to give a name as y0. I'm going to start counting at 0. The next one, y1. The next one, y2, and so on, y3, and then dot, 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 all the way to the last one, y sub n, because my last one is the nth, 1. The one before that is y sub n minus 1. The one before that is y sub n minus 2. These represent the heights, okay, or the function values evaluated at that point. But they also serve as the basis for the trapezoid. Let's take a look at the first trapezoid here. Let me highlight it in yellow here so you can see a little bit better. Okay, so the height of the trapezoid is b minus a divided by n. Again, the height is right here, the distance between these parallel sides. That's the height, that's h. Okay, that's going to be b minus a divided by n. That's going to be equal to h here. And the bases are y0 and y1. But what we want to do is approximate the curve, the area underneath the curve and above the x-axis from a to b. So what I need to do is come up with a way to find the height, or excuse me, the area of each trapezoid and simply add them up. And that's my plan. Okay, so I'm going to take the sum of the areas, and that's going to be the area of the trapezoid 1 plus the area of trapezoid 2 plus the area of trapezoid 3 and so on. So I'm going to put dot, 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 all the way to the nth trapezoid. So the area of trapezoid n, or the nth one. I'm going to add them up. And this is going to be equal to 1/2, and again, the formula is right up here. Let me highlight it. The height divided by 2 times the sum of the bases, where in this case the bases are vertical. Okay, so let's work on that. I'm going to take the area of the first trapezoid, which is going to be 1/2, times the height, which is always b minus a divided by n, because we're going to divide it up in n equal parts. That's going to be specified. And the endpoints of the intervals are also going to be specified. Well, hang on, I'll pause the video for a second. Something happened here. Okay, I'm not exactly sure what happened computer-wise, but let me continue here. We want to add up the areas of the trapezoid, so add up area of trapezoid 1 plus trapezoid 2 plus trapezoid 3 plus all the way to the area of the nth trapezoid. Okay, to do that, I'm going to take 1/2 times the height of it. Taking the height divided by 2 is the same thing as 1/2 the height of b minus a divided by n times the sum of their bases. Now, on the first trapezoid, the bases are y0 and y1. So I have to add up y0 and y1. That's the area of the first trapezoid, plus the area of the second one, which is 1/2 times the height. And the heights are all the same because the widths of the intervals are all the same. So it's b minus a divided by n times the sum of its bases. Now the second trapezoid is right here in blue. Its bases are y1 and y2. So times the sum of the bases, y1 plus y2, plus the area of the third trapezoid. And the third trapezoid is right adjacent to the next one. And you keep on going, you keep on doing that, and you add it to the nth trapezoid, which is right here in yellow, so the first and the last. So the last one is found the same way, 1/2 times the height, which is, again, this is the height right here, and that's h, but h is b minus a divided by n, times the sum of its bases, y sub n minus 1 plus y sub n. Okay, now, let me take this away, you don't need this. What's in common here? Because this big expression here, although it looks complicated, can be simplified greatly if you understand it. So notice that the 1/2 times b minus a over n is all in common. Okay, it's here, it's here, it's here. It's involved in every single area. So what I can do is I can factor it out. So 1/2 times the width, b minus a divided by n, or 1/2 the height, which is b minus a divided by n, times what's left over. And, well, what's left over? Well, it's y0 plus y1 plus y1 plus y2. I'm looking here now. Here, here, and all the stuff in between, and then here. Plus dot 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 plus y sub n minus 1 plus y sub n. Okay, now what's really going on in here? Well, if you notice, by looking at the drawing up here, that for every trapezoid, it shares, well, all trapezoids share a base, and because of that, y1 is shared, and it's going to be added twice. y2 is shared between the second and third trapezoid, so it's used twice. y3 is used twice. All y values, or all the bases, are used twice except the first y value and the last, because they're on the outermost part of the interval. So all of these numbers in here are doubled, or used twice. So if you know that, well, and if you understand that, you could take 1/2 times b minus a divided by n times y0, because it's only used once, plus 2 times y1, plus 2 times y2, plus 2 times y3, and so on, all the way up to 2 times y sub n minus 1, the term before it, or the term before the last one, plus y sub n, where these just happen to be the function values at these points. When you can use that to get the area underneath the curve using trapezoids. So we want to commit this to memory. Okay? So let's apply it here. So on example number 1 here, what I'm saying when I say approximate the area given by the integral of x squared dx from 1 to 2 using 4 trapezoids is I'm saying, hey, our function is x squared. So we have a function y equals x squared here. If we graph it, it looks like this. I'm just approximating the graph here. Y equals x squared starts at the origin here. When x is 1, y is 1, so we have a point here. When x is 2, y is 2, 2 squared is 4, so 1, 2, 3, 4, so 4 here. 1, 2, 3. It's roughly here. You draw the graph, and of course it's reflected on this side. Okay, that's the nature of parabolas here. So it's a parabola. And what we're concerned with is the area underneath the curve from 1 to 2. So in this region right here, where a equals 1 and b equals 2. Those are upper and lower bounds. So what we want to do is divide this into 4 equal parts. What would the width be? Well, let's see. The height of the trapezoids be minus a divided by n. And that's going to be 2 minus 1 divided by 4, because we're using 4 trapezoids. And that'd be 1/4. So this is the height of the trapezoid, or the width of the interval. Height of trapezoid, or it can be considered the width of the interval. Okay, so divide it up into 4 equal parts. So our trapezoids are going to look like this here. So we're going to have 4 trapezoids. The width of them is the interval at 1/4. So what we need to do is set up a table of values and calculate some. Oops, I didn't mean to use the arrow tool. I'll just use the segment tool here. And we want to calculate what y would be when x is something between 1 and 2. Right? Remember, x or y is our function here. It's x squared. So starting with 1, okay, because here a is 1, counting by 1/4, 1 and a 4th, 1 and a 4th, that's going to be 5/4. 1 and 2/4, or 1 and a half, that's going to be 3/2. 1 and 3/4 is going to be our next one, and then 2. So in between each one of these is a trapezoid. So we have 5 values, and in between each of these values is a trapezoid. And again, the width of them from here to here is the height of the trapezoid. The function values are the bases, actually. So let's evaluate first and then use the formula and apply it. So when x is 1, y is 1. When x is 5/4, y is 25/16. When x is 3/2, you get y equals 9/4. When x is 1 3/4 or 7/4, you get y to be equal to 49/16. And then when x is 2, y is 4. Now what this formula is saying is that this right here is y0, that's your first y value, okay? And this is y1, and this is y2, and this is y3, and this is y4. And there are actually 5 values because we started at 0, not 1. And the first and last values are not doubled. Everything in between are doubled. That's what these 2's represent. I'm talking about here, 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 and here. All the function values are doubled in between except the first and the last. So my approximate area from 1 to 2 of y equals x squared would be 1/2 times the height, which is 1/4, times the sum of times the first one, plus 2 times the second one, which is 25/16, plus 2 times the third one, which is 9/4. This is 9/4 right here, plus 2 times the third one, 49/16, plus 4. And you have to simplify this. So 1/2 times 1/4 is 1/8. And you get 1, and then plus the 4, that gives you the 5, plus all these other ones, plus, I just brought the 4 in front. 50/16. See, 50/16 plus 18. Let me see, 18 times 4. Let's see, it's 72. So let me write that as 72/16. And you know what? I'm just going to keep it as 18. I don't want to confuse anybody. So 18/4, excuse me. And then plus 2 times 49 is 98. So 98/16. So what do you get? So you get 1/8 times 5 plus, see, this right here is 50/16 plus 4 times 18 is 72. 72/16 plus 98/16. So it's 1/8 times quantity 5 plus 98 and 72 is 160 plus 10. 170 plus 50 is 220. So 220 divided by 16. And let me see. 5 times 16 is 50 and 30, 80. So this is 80/16 plus 220/16. And that's going to be 300/16 times 1/8. We should simplify this. Divide both by 2, 4. This becomes 2. And divide this by 4, that's 75. Yeah, okay, and so we get is 75/32, and that's approximately 2.344. Okay, now, if you didn't believe me, let's just make sure you do. Let's get the calculator here, let's turn it on. Alright, 75 divided by 32 is 2.34. Okay, now, let's compare that to the exact area, because the exact area is found by integration. So let's do that. The exact area is the integral from 1 to 2 of x squared dx, and that's x cubed divided by 3 evaluated from 1 to 2, and that's going to be equal to 9/3 minus 1/3, which is 8/3, which is 2 2/3, which is equal to 2.3 bar. And if you compare the two, 2.3 bar, which is 2.3 repeating, and 2.34 is very close. Very close. So that's good. All right, trapezoid area formula, the trapezoid technique, does it very well for approximating area underneath the curve using only 4 trapezoids. You couldn't get that close using rectangles, even if you used the midpoint formula. So what I want you to do now is to take a look at the next set of problems, give it a shot, and always compare your approximations with the exact area by actually evaluating the definite integral. All right, good luck, and I'll see you tomorrow.